Hello, my name is Rachel Lemnitzer, and I will be presenting my research on the one-dimensional finite difference time domain in dispersive media for biomedical imaging applications. The motivation of this project stemmed from the trade-offs of biomedical imaging applications, which present either high contrast or high resolution. MRI is an example of technology that only presents high contrast and therefore less accurate detection of such things as cancer. The other motivation for the project stemmed from wanting to investigate the exposure limits of wireless biomedical imaging technologies for patients. There were two stages of the project. First stage consisted of analyzing the relative permittivity and conductivity of over 45 biological tissues using the Debye model. Stage 2 involved using these Debye coefficients to analyze a multiphysics head model using one-dimensional finite difference time domain. This slide shows the dielectric properties, the permittivity and conductivity that were gathered for each of the tissues over a frequency of 100 megahertz to 100 gigahertz. Using these permittivities and conductivities, the Debye model was used to generate the complex permittivities for the tissues using a certain number of poles as well as relaxation time to generate, in this case, 3-term Debye coefficients to reduce the heavy computations that you would normally see for such a wide range and high range of frequencies. This slide shows the figures generated for the dielectric properties as well as the Debye coefficients. This shows a comparison of the aorta tissue between the simulation and the measured data and shows very accurate fitting. The error in this case did not exceed 1.252%, and overall for all the tissues the errors did not exceed 4%. The second stage of the project used these Debye coefficients to analyze a head model using a layer A model with no eye tissue and a layer B model with eye tissue to analyze the safe exposure limits of specific absorption rate as well as temperature rise through the model. This shows the local SAR distribution for layer A model. This shows the local SAR distribution for the layer B model with values that are less than the layer A model. This slide shows the temperature rise distribution for the layer A model and for the B model. Neither case exceeded 1.03 degrees Celsius. And overall, this project was great for understanding and using the dielectric properties of over 45 biological tissues, using the Debye model with high accuracy, and then using these Debye coefficients to analyze a head model using the finite difference time domain method to analyze the specific absorption rate limits of the tissues, which did not exceed the exposure limits of 1.6 watts per kilogram. And in the future, the project will extend to using other areas of the body and analyzing them using the Debye coefficients, as well as this finite difference time domain method.